free falling, and I'm free. All right, so free fall. What's up with that? Nothing's down. Well, no, that's not true because free fall means situations where you have an object that is only under the influence of gravity. So we're ignoring air resistance and other things that would make it more complicated for us. So that's good. So what that means is that your acceleration is going to be, in the ball toss lab, you should have got in your velocity time graph should have looked something like this, and your slope should have been approximately negative 10 meters per second. The actual acceleration due to free fall about at the surface of our planet is about negative 9.8 meters per second. But to make things a little bit easier for calculation purposes, we're going to just go with negative 10. It'll be a little bit easier for us to deal with. So that's what this means. It means that we have an acceleration of negative 10 meters per second, or you can write that as meters per second squared if you want. And when we set up our little table, like in number 1, for example, I know that I'm going to have acceleration, initial velocity, final velocity, displacement. Now right here, instead of delta x, when I think x, and when you think x, because of your math training, you probably think of x as being something that goes back and forth like this. And these are all problems where we got something going up and down. So I'm just going to call it delta y here. But all of the equations are the same. I'm just going to write everywhere where there was a delta x in my kinematics equations, I'm just going to write a delta y instead. All right, and then time. So in these free fall problems, since we know that the acceleration is going to be negative 10, it's just that. We get that for free if it's a free fall problem. So that's going to be negative 10. I don't even have to read the problem. I know this is a free fall problem because it says that right here at the top of the sheet. All right, so what do we got here? A stone is thrown upward and it rises to a height of 20 meters. So look at the units and be careful. Don't forget to think. 20 meters, and it rises. So that means the displacement of it is going 20 meters up. Right, that's the displacement. And it rises to a height of 20 meters. Now, if you're stuck here and you're looking at these going, okay, I got this because I know it's free fall, so that's negative 10, and then I got the displacement's 20, but I need something else. Now, it doesn't say anything about the time, and it doesn't say anything about how fast it was thrown. So this time, how fast it was thrown. So there must be something that I know about this that we're not thinking of right here. And it's often the case, I've seen many times with students in this class, this is a tricky thing to spot because if we're throwing it and this is like its maximum height, it's going to be going fast and then slower and then slower, and it's going to get to a peak. And right at that peak, its velocity is 0. Right? That's what makes it the peak, because the velocity goes from up, positive, to down, negative. And as it crosses from positive to negative, it must just for an instant at the top there be 0. So that was the missing piece. Okay, so with what speed was it thrown? That's this. So for the first part, I need the equation that relates those things. So looking at my equation sheet of kinematics equations. Oops, it's supposed to be plus there, sorry. That's this one. So I'm always going to write down the equation before I use it. And I'm going to drop the units just to keep things clean here. So looks like my initial velocity, 2 times 10 is 20, times 20 is 400. And the square root of 400 is 20. So it was thrown up at 20 meters per second. That's for part A. for part B. How long does it take? So that's the time, so that would be the equation that has these things in it. So let's see. Well, I also have this, so actually you could use any equation you want at this point because you already have that. So I could use VF is equal to AT plus VI. I know the VF is 0, the acceleration is -10, the time is what I'm looking for, plus the VI is 20, so that looks like time is going to be 2 seconds. All right. Not too bad. So for number 2, stone is thrown straight upward with a speed of 20 meters per second. That's exactly like the last problem. But delta y time. But in this problem, it's caught on its way down at a point that is 5 meters above where it was thrown. So you can imagine it's going up like this and then back down again, and then somebody or something is stopping it there. It's getting caught like 5 meters above. So that means its displacement from the difference between where it started and where it ends is plus 5. It's 5 meters higher at the end than where it started. So that means my delta y is 5 meters. Okay? How fast was it going when it was caught? When it's caught, that's the final velocity here. So that's those things. So it looks like that. Again, final velocity, that's what I'm looking for. Initial is 20 plus 2 times -10 times 5. So let's see, that's 100, so 400 minus 100 is 300. That's about 17, I think. Whatever the square root of 300 is. Near enough to 17 meters per second. And for B, let's see, how long did this take? So looking for time. You could really use any equation that you want now that you have this. I'm going to use the one that does not have VF in it. So that's delta y is equal to 1/2 AT squared plus VI t. My delta y is 5. 1/2 A is always -10, so 1/2 A is -5. T squared, that's the time I'm looking for. The VI is 20t. Now I wanted to use this equation because I wanted to show you what to do when you end up with a little quadratic equation like that. I do not want you to use the quadratic formula. I bet you don't really want to use the quadratic formula either, do you? So what I want you to do is know how to deal with this. When you get a t squared and a t in your equation, get everything onto one side like this, and then graph that and look for the zeros of it. So I'm going to graph this, -5. My calculator wants to use x instead of t, but that's fine. 20, just a name for the variable. All right, so I'm going to put that in there, and then I'm going to go, I'm looking for, I definitely don't want any negative times, so before I hit graph, I'm going to go to my window. I'm looking for a time between 0 and 10, that's probably good. Now these y values, this is real super close to the y-axis, but I actually don't care. I don't need to see the whole picture of this. I just want to see where it crosses. So if the time is between 0 and 10, then I should be able to see it on this graph. And you can see there's actually 2 places where it crosses. So before I go deciding which one of those is my answer, let's think about what's going on here. How long does it take for this what is it, stone, for the stone to go up and then back down to here. Well, this equation right here is the equation that's going to give you the time for when the displacement is positive 5. But that actually happens 2 times, right? Because on the way up here, oh, I'm pointing, some of you can't see, there it is. On the way up, it passes this 5 mark, right? Right there, its displacement would be plus 5. And then it goes up and comes back down again, and its displacement is plus 5. So it happens 2 times, and we're interested in the second one, like when it goes up and comes back down to there. So that's this right here. Do you know how to find that with your calculator? Well, it's between 1, 2, 3. It's between 3 and 4. I'm going to go second, calculate right there. I'm looking for the 0. Now it's going to ask me for a left boundary and a right boundary. It's asking me where it should look, in other words. And I know that it's just by looking at the graph, it's between 3 and 4. So I'm going to enter 3 as the left bound. I typed 3, enter. And then I'm going to enter 4 as the right bound. So I know it's in between those two. You can see it made little arrows showing me in between. And then I'm going to enter one more time. And it's going to tell me it's about 3.7 seconds. All right, let's do 3 and 4. So 3, at the instant that a hot air balloon is 300 meters above the ground and rising at 13 meters per second, a ballast bag, that's those, I don't know if you've ever seen a hot air balloon, they have those like sandbag kind of things hanging off the side, so if you need to get more up going on, you cut the ropes on those and you drop the bags. A ballast bag is released from the balloon. Okay, so it's rising, so this means that the bag here, if the balloon's going up like this and you cut the rope on that bag, the initial velocity of the bag was going the same speed, it was attached to the balloon, so its initial velocity is this. That is the initial velocity of the bag, right? Just like if you're like holding an apple core out the window of your car and then all of a sudden you drop the apple core, it doesn't drop straight to the ground because it was moving with you in the car. Its initial velocity is as fast as the car was going, right? That makes sense? It's like when you throw a baseball, when you let go of the baseball doesn't drop straight to the ground. It's moving exactly as fast as your hand was moving at the instant that you let go of it. All right, so if you didn't get that, if you didn't figure that out the first time you looked at this problem, then probably you should pause the video now and say, oh, okay, if that's the initial velocity of the bag, like, can you do the rest of it on your own from here? So try that, and then you can check back in here in a minute. So here, part A, describe the motion of the bag the instant it is released from the balloon. Well, that's, I guess, what we just did, isn't it? The initial velocity is 13 meters per second. And that's positive. It's going up, right? Just to be sure we understand that. To what maximum height from the release point does the bag travel? So if we're only paying attention to like where it was released from, in other words, I'm ignoring the fact that it was already 300 meters above the ground. They're just saying like from the release point. So let's see. I know my acceleration. Once you let go of that bag, once you cut that rope, it's got that -10 acceleration. Its initial velocity, just talked about that, that's 13. Its final velocity, if we're interested in to what maximum height, remember, that happens when the final velocity is 0. It's real easy to miss that. And then delta y, that's what I'm looking for. I'll write time down there just to be thorough and have the complete list. So right now I'm interested in this. So that looks like I need the VF squared equals VI squared plus 2A delta y. So that's 0 is equal to 13 squared plus 2 times -10 is delta y. So let's do some math here real quick. It's about 8.5 meters. This is a displacement. 8.5 meters. What is the velocity of the bag 5 seconds after it's released? Okay, so that is a new set of, so that means we're not talking about it at its peak anymore. We're talking about this being 5. So what would the final velocity be at 5 seconds after it's released? So part C, sorry, I'm trying to cram too much in here. We better move on to a little bit of fresh paper territory here. How about here? So what is this, part C? So what is that velocity of it 5 seconds after it's released? So that's negative 37 meters per second. And that's what the acceleration due to gravity does. It subtracts 10 from your velocity every second that goes by. So this thing started with a velocity of 13 meters per second. After 1 second, it would be 3. After 2 seconds, it would be negative 7, so it would have peaked and turned around. After another second, it would be negative 17, and so on. So after 5 seconds, it's that. D, what is the position of the bag 5 seconds after it's released? Well, delta y is equal to 1/2 at squared plus vit. That's 1/2 times the negative 10. And 5 seconds after it's released, plus VIT. So let's see, that's negative, doing some math. Okay, so delta y is negative 60. This was a test question and you did all this and got that answer, you'd get everything except 1 or maybe 2 points. But that's actually not the answer to the question that's being asked here. The question is, what's the position of the bag? So it's 60 meters lower. This is the change in position, right? That's delta y. So the change in position being negative 60, that means it's 60 meters lower than where it started. And where did it start? 300 meters above the ground. So the position, which is just y, not delta y, is equal to 240 meters. 300 meters plus that, plus negative 60 or minus 60. How long does it take for the bag to reach the ground from the instant that it was released? So if it's going to make it all the way to the ground, that means it would have to have a displacement of 300 meters, but 300 meters down. So that means its acceleration is negative 10, of course. Its initial velocity is 13. Its final velocity, you think its final velocity would be 0 because it gets to the ground? No, that is not what final velocity means. Final velocity is how fast it's going when it gets to the ground. So final velocity, we don't know, and the delta y is 300 meters, but it's down. And again, I talk about all these mistakes that physics students of the past have made. This is a really easy thing to forget, that negative sign. The displacement is 300 meters, but it's going from where it started down 300 meters. So, got to be careful there. And time is what we're looking for. So, what's the equation that has those things? It's the delta y is 1/2 at squared plus VIT. Might have to do a little graphing again. My calculator. 1/2 times the acceleration is negative 5 t squared plus 13t. So let's see. So I got a similar equation here. I can just edit this one, 13, and then it's going to be plus 300 this time. Right? Why did it end up being plus? Because it was negative over here, and I added it over to that side. Do you think that happens in 10 seconds? Let's see. Oh, barely. So it looks like it's a little bit bigger than 9 seconds. I think I'll do 8 and 10 as my upper and lower bound, just to be sure. Now, what would you do if this screen came up and it was blank? Well, two possibilities there. The most likely, if you didn't make any other mistake, is that it happened after 10 seconds, so then you would just have to go back and make this a bigger number. The other possibility, of course, is that you made some kind of mistake, and you have to go back and figure out what that was. So left bound, I'm going to go between 8 and 10. 8 and 10. Looks like we got about 9.2 seconds. Cool. All right, one more. Let's do it down in this corner here. We've got stone is thrown straight upward with an initial velocity of 8 meters per second. And from the edge of a 100-meter tall building, and it lands on the ground below. So that means if it starts on top of a 100-meter building and then lands all the way down here, it's going from 100 down to 0, so its displacement is negative 100. If you're wondering to yourself, wait, what about the up part of that? You didn't count that because it's going to go up first, so it'll be more than 100. No, wrong, because displacement is only the difference between where did it end and where did it start. That's what displacement is. So we're going from 100 to 0. What happened in between? Don't care. We're going from 100 down to 0. That's a displacement of negative 100. Of course, this is free fall, so we get this for free. And we want to know first how long is the stone in the air. That's a time here, so that's like what we were just doing a minute ago. Delta y equals 1/2 a t squared plus VIT. So delta y is negative 100. 1/2 a is negative 5. T squared. VI is 8. It's t. So same dealio here that we saw in the last couple problems. I'm going to have to get out the trusty calculator again. So I got the negative 5x squared. This time it's going to be 8x and plus 100. Take a look at that graph. There it is. And let's see, we got 1, 2, 3, 4, 5, 6. In between 5 and 6. Looking for that 0 in between 5 and 6. About 5.3 seconds. And last, what is the speed of the stone when it reaches the ground? So if we only wanted to use these pieces of information, of course we do have the time now, so you do have options here. I could do the VF squared as VI squared plus 2a delta y. So VF, that's what we're looking for. VI squared plus 2a delta y. Can't forget that negative sign. And let's see, so that's technological difficulties here, which just means I'm pushing the wrong. I'm trying to drive my calculator with my left hand. Not going very well. I think I got it under control now. So let's see. Just doing some math here. So I got VF. Now I took the square root of something, so you know from algebra class that that's going to give you plus or minus. So I got about plus or minus 45 meters per second. Now, of course, this rock, this stone here, can't be going up and down. It's one or the other. So how do you know which one is right? Well, you think about the problem, and it's going to be very obvious which one is correct. What's the speed of the stone when it reaches the ground? Well, is it going up or down when it reaches the ground? It's going to be going down. So the velocity is negative 45 meters per second, and the speed, which is how fast is it going, I don't care about direction, is just 45 meters per second. If you made a sign mistake there at the end of that problem, that's like a 1-point error. Not a big deal at all. All right, there's that free fall worksheet 1.